Now let's talk about some of the concepts that we have looked at when we've been talking about these confidence intervals and hypothesis testing. So the alpha is the level that corresponds to a critical z value. It's where we're calling things weird if it exceeds that z, or consequently the p would be less than alpha. So I said, most of the time, if you are not given an alpha in the problem, default to the 0.05. For a one-sided test, it has a critical z of 1.645, and the two-sided test would have a critical z of 1.96. Let's see how we get that. So when I'm one-sided, the critical z value goes here, and all of the alpha is here. When it's two-sided, we have a positive and negative critical value, and half the alpha goes in each place. So if I'm talking about 0.05, all of the 0.05 is here. So to get that area under the curve, because it's a z value, I would do inverse norm of the area I want, 0.05. And then remember, with z values, the mean is at 0 and the standard deviation is 1. And then over here, it would be the same thing, except we're dividing the 0.05 in half, so that would be 0.025 here. And then by symmetry, this would be a 0.025 the same. But once I find this critical value, I can just make it positive to find this one by the symmetry. All right, so let's do that inverse norm, and let's see how we're getting it. So if I go over here to my calculator, and I hit second distribution, and option 3, and type in that area being 0.05, and the mean is a 0, and the standard deviation is a 1, and then I paste in there, I get that critical value of negative 1.645. Okay, so for one-sided, it's 1.645. Negative if it's to the left, positive to the right, because it's the same by symmetry. Now, let's do it again, but let's change that area from 0.05 to 0.025 for the two-sided test here. And so we're going to insert second, insert a 2. And there's our 1.96. So notice that's how we're getting all of these values. I would do the same thing for this area or this area to get these values over here. So these are the critical z's that correspond to these alpha values. Now, when we perform a hypothesis test, we can make mistakes in two ways. Either the null hypothesis is true, but we mistakenly reject it. That's a type 1 error. Probability of making a type 1 error is alpha. Or the null hypothesis is false, but we fail to reject it. That's a type 2 error, and the probability of making a type 2 error is beta. Here's a diagram of what can actually happen when we're doing a hypothesis test. If the null hypothesis is true and we fail to reject it, we did the right thing. If the null hypothesis is true but we reject it, that's a type 1 error. If the null hypothesis is false and we reject it, we did the right thing. If the null hypothesis is false and we fail to reject it, that's a type 2 error. All right, so let's look at a situation, put that into context. So let's go over here. Testing for Alzheimer's disease can be a long and expensive process consisting of lengthy tests and medical diagnoses. Recently, a group of researchers devised a 7-minute test to serve as a quick screen for the disease for use in the general population of senior citizens. A patient who tested positive would then go through more expensive battery of tests and medical diagnosis. The author reported a false positive rate of 0.4 and a false negative rate of 0.8. Put this in the context of a hypothesis test. What's the null and alternative hypothesis? Well, my null hypothesis would be, I'm going to assume I'm dealing with a healthy individual. So the null hypothesis is that there's no Alzheimer's disease present. The alternative hypothesis would then be my patient has Alzheimer's disease. What would a type 1 error mean? Let's look back at that. Remember, a type 1 is where the null is true, that I'm dealing with a healthy individual, but I say that's not the case. So it would be a false positive. I would diagnose, I would say that we have, a positive on this test. Now, what does that mean? That means that we would send them off for more testing. because we believe that they may have Alzheimer's disease. What would a type 2 error mean? So now a type 2 error, if you remember, the null is false. So I don't have a healthy individual, but I don't recognize it. So I have someone with an Alzheimer's disease and I missed it. That's a false negative. So the false negative would mean we missed the diagnosis. Which is worse here, a type 1 or a type 2 error? Well, if a type 1 error is made, I send a healthy individual on for more testing. It's going to cost them money, and they're going to have more pain and discomfort from going through more tests. But a type 2 error would mean I don't send them for testing when really I should have, because they actually have the disease. So we're letting somebody go undiagnosed with Alzheimer's. Which is worse? Probably the undiagnosed person. I would much rather a healthy individual undergo more rigorous testing than mistreating somebody who actually needs the treatment. What's the power of this test? So now let's talk about power, and that's on my next slide here. So a type 1 error is how often it happens is the alpha value. So notice here, type 1 error occurs 4%. That's what we're getting at there, okay? Now, the power is 1 minus beta. It's a test's ability to detect a false hypothesis. So here, my beta, remember I told you back up here, beta is the probability of a type 2 error. We said for this particular problem, type 2 error is a false negative. So it's 0.08. Beta is 0.08. The power is 1 minus beta, so 1 minus 0.08 would be a 0.92. 92% in that we're actually going to do a correct detection of making sure that we get that false hypothesis, okay? All right, guys, we'll talk to you in the next video.